Hello everyone. In this video we're going to talk about the action potential. So this is for anyone who's in an introductory neuroscience class, or maybe you're more advanced and you just want a review of the basic concepts. So let's let's draw a neuron, or at least attempt to. So you have the axon, and then it's going to be a bipolar neuron. So it'll have little dendrites. Okay, very ugly looking dendrite. Hold on. Okay. So imagine these are dendrites, and then we have the cell body and the nucleus here. Now, if I were to kind of zoom in on the cell membrane of this neuron, you would see something like this. All right. So these are, what I'm drawing here are the phospholipid heads, right? These are the heads like the water, and the tails do not like the water. And so they should be facing inward, not outward, toward each other. This is just basic cell biology. Now, what you're going to have in the spaces where I've left empty, you're going to have ion channels. So these ion channels, let's do... So what I'm drawing here in purple is going to be one type of ion channel, and in red is you have another type of ion channel. So these are going to allow ions to pass through the membrane. Now, when we are at rest, meaning the neuron is not doing anything, it's not firing, we're generally going to have more sodium outside, okay? Sodium outside. And we're also going to have some, let's do them in green. Let's favorite this so we can use it later. I don't know where it went. Why did my app crash? Why is everything I drew just... Wait, what happened? Bro, I was doing good. Okay, well, we're back. Okay. Sorry, my app crashed. Okay. So, here, we have chloride ions on the outside, and we also have sodium ions on the outside. We still have some on the inside, but they're more abundant on the outside when we're at rest. So the neuron is not firing. It's not doing anything. It's just sitting there. We have also more potassium ions on the inside. And we also have just negatively charged proteins and organic molecules that are negatively charged on the inside. Now there's going to be a lot of proteins and a lot of organic molecules. So relative to the outside, the inside is going to be negative, more negative than the outside. So this is where we want to introduce the concept of membrane potential. And so this is a graph showing membrane potential in the unit of millivolts over time. So you want to kind of realize that this is usually going to be milliseconds. And so don't worry about this unit. Just understand that membrane potential means how much more positive is the inside relative to the outside. So if we have a lot of proteins that are negatively charged, this is going to be negative. So when the neuron is not doing anything, the resting membrane potential is negative 70 millivolts. Okay? So when we're not doing anything, when we're at rest, it's negative 70. Now, how does an action potential actually occur? The sodium channel right here is usually going to be closed off. Okay? Potassium can flow in and out, but it doesn't really change it very much for now. What can happen is that neurotransmitters, and more specifically excitatory neurotransmitters, or any ligand really. So excitatory neurotransmitter on a receptor that's excitatory. Don't worry too much about that, but basically neurotransmitter comes in and binds to this receptor. Let's make the neurotransmitter, let's make that like this. Imagine neurotransmitter comes here and binds. That will cause the sodium channel to open. So then it opens. Then sodium ions, which are like this, will flow into the cell. Now remember what we said, right? Membrane potential is what is the charge here inside the cell relative to the outside of the cell. If we have sodium coming in, which is positive, it's going to make the inside more positive. So then the membrane potential will also become more positive. Right? It will go up. Now, if it goes up enough, if it goes up to negative 55, that is the threshold generally the threshold for neurons for firing. So once it hits negative 55, then what will happen is that a lot of other sodium channels are also going to open. So the way in which this happens is this. You're going to have like another cell coming in, and let's say it synapses onto our little neuron we drew. And it releases the neurotransmitters, as excitatory neurotransmitters that we saw, and sodium flows in, right? But this one synapse is only going to have a very small effect on the entire neuron, right? If you have more synapses, which you usually do, right? Let's say we have more synapses, and let's say we have more excitatory neurotransmitter, right? And let's say we have another one. And this one also makes more sodium into the cell. If we put in enough sodium into the cell and make the membrane potential go up enough, at some point it'll reach negative 55. And once it reaches negative 55, there are certain group of receptors on this area of the neuron called the axon hillock. So this is axon hillock. This area is going to have a lot of what's called voltage-gated sodium channels. So let's see what that means. Voltage-gated means that if the voltage or the potential goes high enough, these sodium channels will open. So these are these sodium channels that are kind of sitting over here. And they basically sit around and they say, okay, we're going to do nothing if the membrane potential is really low. Let's say if it's like negative 70. But once it hits negative 55, we're all going to open and we're all going to let our sodium ions come into the cell. So let's say that these other neurons, right, they give us enough sodium and they make the potential go high up enough to the point where these voltage-gated sodium channels on the axon hillock say, okay, we're going to let sodium in, right, because the membrane potential is going high enough. When the membrane potential goes up, we call that depolarization. Okay, so depolarization happens when we let sodium in. So if the cell is depolarized enough, these will open. Once these open and we've hit threshold and those open, we're going to start the action potential. So what will happen is that these voltage-gated sodium channels are going to allow a lot of other sodium channels open. So we're going to get a lot of sodium into the cell. So even more than before, like a lot more, right? Through the same channels here, but more so over here, right? So this will cause a massive depolarization of the cell. The membrane potential is going to shoot way up. And here we have 0. But then here we have the stage where we hit about positive 30 millivolts. This is the point at which this cascade kind of stops. We stop getting this sodium into the cell. So this stage that we've talked about is called the rising phase. This is where sodium enters the cell and we depolarize. Then we have the peak. which is over here. Now, what happens at the peak? At the peak, there's a certain protein. Let's do it in blue. Okay. It comes in and basically kind of comes over here and moves in the way of the sodium ions. So if I drew it, it would look like this, right? It comes in and blocks these sodium ions from coming in. So the sodium can no longer come in. It basically blocks the sodium channel. So the sodium channel is not necessarily closed, but it's inactivated, right? Sodium just cannot flow through there because of a physical barrier of this little protein. So we're not going to keep going up, right? Our sodium is not going to keep coming in. We're not going to keep depolarizing. Instead, we're actually going to go down, right? So how are we going to go down, right? If we want to go down, something either negative has to come in or something positive is going to go out. What's going to happen is that potassium ions are going to be like, ooh, it's really positively charged in here now that there's sodium inside. And we can move this. Excuse me. Now there's sodium inside. So, these potassium ions are going to start leaving through these potassium channels, right? So they're going to start leaving. And so because positive charge leaves, the net effect is that the inside of the cells is going to become more negatively charged. So we're going to become more negative in this phase called the falling phase. And then we're going to actually hit threshold again, but we're going to actually undershoot. So we're actually going to go below threshold, then we're going to go back up and go back to resting potential. So this undershoot here is called hyperpolarization. We're becoming really polarized or really negative. So what happens when we hyperpolarize is that too much potassium goes out of the cell, but then a little bit of it comes back in. So now we have a situation at this point. At this point in the cycle where sodium is inside. Potassium, a lot of it has gone outside. So now we're left with a situation where it's backwards of what it was initially. Sodium was outside, potassium was inside. So how do we fix this? Well, first of all, this little protein that we had that blocked the sodium channel is just going to go away. We're going to close the sodium channel normally, and we're not going to have any neurotransmitter binding, so this is just gone. But then we have what are called sodium-potassium pumps, which I didn't draw. So I'm going to try to do it here. Let's do it in green. So a sodium-potassium pump is a kind of protein that will use energy. And what it does is it pumps sodium out and potassium in to restore the original situation. And specifically, it pumps, I don't remember the numbers, so I have to look them up. Yeah, it pumps 3 sodium ions out. So for one cycle, it pumps 3 sodium ions out and 2 potassium ions in. So the net effect is that it's going to become a little more negative. But this is going to basically make it so that the cell is maintain the original ratio of ions. So once this finishes doing its thing, we're going to have more sodium outside and more potassium inside. And we're back at the same rest again. So this whole thing that we just explained, from here to here, is the action potential. So what will happen during the action potential is that what happened during it was sodium came in, potassium went out. Right? That's basically the what happened. That exact thing is going to happen at this axonal segment. Sodium comes in, potassium goes out. At the next axonal segment, sodium comes in, potassium goes out. At the next axonal segment, and on until we hit the axon terminal, at which point, once we hit the axon terminal, this action potential is going to cause a opening of calcium channels, and then calcium will bind to neurotransmitter vesicles, and then these vesicles will bind to the membrane like this, and they will release their neurochemicals to the synapse, and then another neuron will be stimulated. So it's basically how that works. So when people say an action potential travels down an axon, it's not really that anything is moving like this. It's that this cascade of events of sodium moving in and potassium moving out keeps happening at every successive axonal segment. That's if the axon is unmyelinated, right? It has to happen everywhere. If it's myelinated, let's draw another axon that's myelinated. Let's use yellow for myelin, right? So let's say, didn't really complete my axon there. Okay. If the axon is myelinated, that process is only going to happen at the nodes of Ranvier. So, meaning that, let's draw another one. Here, sodium goes out, potassium goes in. It doesn't have to happen at every little segment. It can happen now here, and then imagining that there's myelin on the other side. It can happen here, and then here. So that actually makes the conduction faster because you don't have to keep doing this process everywhere painstakingly until you hit the end. So that's the action potential as best as I can explain it. Hope you learned how it works, and thank you for watching.